Hello, this video is for Stat 310 Handout 7, Part A. This video will cover pages 1 through 9. Okay, let's go ahead and get started then. So what Handout 7 is about is making comparisons for means across groups, so like analysis of variance, except now we have what is called a blocked design, which will be different than Handout 6. So let's talk a little bit about what we mean by a blocked design. So if we consider the sleep deprivation study again, we had this data here that we looked at extensively in Handout 6. We had 4 different treatment levels, which was sleep deprivation. Here you can see the graph that we looked at several different times with each of the averages from the 12, 18, 24, and 30-hour sleep deprivation. And the goal here was to make comparisons across these averages across the 4 different treatment levels or sleep deprivation levels. Before we get into too many more details, we're going to first talk about the design aspects of this study. So in particular, when we talk about experimental design or the design aspects of a study, we are concerned about how the subjects were actually assigned to the sleep deprivation levels. So that influences how we will conduct our analysis. So let's just consider a situation here where I have a total of 32 subjects that need to be assigned to one of these 4 treatment levels, or to the sleep deprivation levels. So, in this type of design, what we might consider is having a hat of 32 total people that are willing to participate in our study. We would randomly pick out 8 of those people, and then they would be assigned the 12-hour sleep deprivation. So person 19, 23, 2, all the way through person 5 would be asked to sleep deprive at 12 hours. We would then randomly select another 8 from our potential pool of people that are willing to be in our study, and they would be assigned to 18-hour sleep deprivation. We would then randomly assign the next 8 and assign them to 24-hour sleep deprivation. And then the remaining 8 would be asked to do 30-hour sleep deprivation. So here I have a total of 32 people, 4 treatment levels, so 8 for each of those. And those 8, would be randomly selected to participate in one of those sleep deprivation levels. Now this particular setup is called a completely randomized design. Okay? So a randomization process, the one that I described up above there, is a completely randomized design. We are assuming that the subjects or the units that are going to participate in this study are similar, or what we say homogeneous. This random assignment ensures that any potential effects due to the individual subjects or units are balanced out across the 4 treatment levels. So that is a very common, it's the most simplified design aspect that we can employ when we're doing a study like this. Okay, let's complicate things a little bit more. Let us suppose that we are going to do a study where I'm interested in the effect of alcohol consumption on reaction time. We have 9 subjects that are available for this study, and we're going to have 3 different treatment levels. A control group that's not going to consume any alcohol, another group that's going to consume 1 ounce of alcohol, and another group that's going to consume 2 ounces of alcohol. What we're interested in is the reaction time. Again, the 3 treatments are no alcohol, 1 ounce, or 2 ounce. Now, one thing that we know about reaction time is that the age of the subject is known to influence reaction times. In particular, younger drivers tend to have faster reaction times than older drivers. This is one issue that comes up when you're talking about older individuals are more likely to be in car accidents. Okay, the cognition level maybe isn't as quick as it is for younger people, and their reaction times are slower. So here, okay, let's keep going forward with trying to do this study. I have 9 people that are willing to participate in my study, but I'm also going to make note of their age. Okay. If I were to just do a completely randomized design, okay, so let us just go forth with a completely randomized design. What that means is I would randomly pick out 3 people and assign them to no alcohol. I would randomly pick out another 3, and they would be assigned to 1 ounce of alcohol, and then lastly, the last remaining 3 would be assigned to 2 ounces of alcohol. I could run the experiment, and let's just suppose that I get these reaction times. When we go to make comparisons, we might end up finding that the 2 ounces of alcohol had the slowest reaction time. So if the data came out like it was here, which I just simply made this data up, but if this data came out like this here, then 2 ounces would have the slowest reaction time. However, up above, I said that I knew that age would influence reaction time. If I now look at what is the average age of my 2 ounce alcohol group, that is almost 60 years old. So what happened here is that some of the older people, not all of them, okay, I have a 60-year-old that got assigned a 1 ounce, but the 2 ounce group got assigned several of the older people here. So the 2 ounce group, okay, appears to have a slower reaction time. Oops, sorry about that. The 2 ounce group looks to have a slower reaction time, but is that because they consume 2 ounces of alcohol? Or is that because older people happen to be put into that treatment group? Notice that the reaction time for the no alcohol group here, slide back up a little bit, the reaction time for the no alcohol group tends to be quite lower. But again, this has the younger people in it. So what I want to do, or what we would want to do in a situation like this, is to not confound age with my treatment. If I know that age is an influencer on reaction time, I want to take that into consideration when I'm trying to assign these treatments. And that is the idea of a blocked design. So let's talk a little bit more about what a blocked design looks like. So this idea, let's real quickly talk about just the confounding variable here. What I need to do to prevent confounding is to get the subjects, okay, whose ages, the design of the alcohol study should be altered to prevent confounding from taking place. We need to get subjects who are similar or homogeneous when we're assigning the treatments. Okay, so when I'm trying to do an analysis and look at alcohol consumption versus reaction time, age here is playing an influence on that, is adversely affecting that relationship that I'm trying to develop. So age would be a confounding variable in this study. And what we want to do is adjust out or adjust for age when I'm doing the random assignment. All right, so a better randomization scheme would reduce the effects of that confounder. So now what I've done here is taken person 2, 4, and 3, set them up on top of my hat just for convenience, and those are all the young people. Person 8, 7, and 9 I'm considering are the middle age, and person 1, 5, and 6 are the older people. Now when I do the randomization, what I'm going to do is just pull off my young people. So that's person 2, 4, and 3 again. and I'm going to assign one of those young people to the no alcohol group. I'm going to assign one of those people to the 1 ounce alcohol, and I'm going to assign one of those young people to the 2 ounce alcohol group. And now, once that is done, I'm going to go to my middle-aged individuals, which are person 8, 7, and 9, it looks like. One of those individuals is going to get assigned to the no alcohol group, one to the 1 ounce and one to the 2 ounce. And likewise for the older group. So I do my randomization, but it's done in a slightly restricted way. In other words, when I go to assign or make a decision about which person is going to get what alcohol treatment, I'm doing that within the young group. Or here I'm doing that within the middle age group. Or in the bottom, I'm doing that within the older individuals. And what this is going to ensure is that I get a young, a middle, and an old person in the non-alcohol group. So that's going to be person 3, 9, and 5. This one here is in the young group, this one here is in the middle age, this one here is in the old group. Likewise, when I'm looking at the 1 ounce, I'm going to have a young person in that group, I'm going to have a middle-aged person, and I'm going to have an old person. That would be person 4, 7, and 1. 4, 7, and 1. And likewise for the old group. So this is what we call a restricted randomization scheme, in that I am restricting how the randomization is being done. This is actually called a balanced randomized block design because there is the same number of replicates for each treatment age combination here. So these are the none young, none middle-aged, none old. There's one person in each of those. So the number of replicates here is actually 1 for each of those combinations. Okay, let's talk about how to graphically visualize this. So inside of JUMP, let me grab JUMP now, open that up. This is what that data is going to look like inside of JUMP. I'm going to have alcohol consumption levels, none, 1 ounce, 2 ounce. And then I have the age groups here. And then the thing that I'm interested in is going to be my reaction time. Now, what we would have done before is done a fit Y by X. Let's look at the reaction times across the alcohol consumption groups. Okay. Oh, wait. One thing I notice here is that we should probably order these treatment levels. So none should be on the left here. So that would be no alcohol, and then 1 ounce, and then 2 ounce. So let's recreate that graph. Let me order those first and then recreate that graph. So what I want to do is order my alcohol consumption. I'm going to do a right click, say column properties, and then value order on those. And then I can put them in the order that I want, which is going to be none, 1 ounce, and 2 ounce here. Say OK. This gives me a little star over here next to my columns. That is indicating that you got some sort of setting on your alcohol consumption variable, which is what I wanted because I want those in a particular order. So now when I go and do analyze fit Y by X, alcohol consumption, reaction time like we've been doing, those should be in the right order. So now I got none, 1 ounce, and 2 ounce. What we have been doing up to this point is just display options and then mean lines, right? However, this display right here does not take into consideration the different age groups, which is something that we want to worry about when we're looking at reaction time. So my blocking variable here is age. We must take that into consideration when we're trying to compare the effect of the alcohol consumption. So to do that, what I want us to do is click on the age here. Well, excuse me, we're going to go rows. We're going to do color or mark by column. And I want to mark by age. So rows, color or mark by column. And I want to select age here. So now the red circles on my plots will be the young people. The green will be the middle-aged people, and the blue will be the older people. So let's say OK. That is going to mark each of these columns, or rows, excuse me. You can see these first three are red because these are my young people. Next three are green because those are my middle-aged. The last are blue because those are my old. Now when I make that graph, reaction time, alcohol consumption, what I want to be looking at here is the red to red to red, the green to green to green, and the blue to blue to blue. I want to actually be looking at those within their colors. The other thing that I can do to help with this is from my red drop down, select matching column, and I want to select the age as my matching column. And then that's going to just simply connect my lines, connect my subjects for each of the different age groups. So again, red is my young people, green middle-aged, blue is the older. Now one thing that I notice right away in this plot is the blue tends to be the highest. Well, that's because they're the old people. We know that their reaction times are higher. And red tends to be the lowest. Well, that's because they're the young people. But what I'm trying to understand is the effect of alcohol on these. So one thing that I see when I'm looking at the effect of alcohol for the young people, it goes up. The reaction time slows down quite a bit when I go from 1 ounce to 2 ounce. Look how much this jumps here from 1 ounce to 2 ounce for the red. Whereas for the green and the blue, it doesn't jump nearly as much. When I go from none up to 1 ounce, it actually looks pretty consistent. So the effect in going from no alcohol to 1 ounce is pretty consistent, okay, regardless of age group here. I mean, this one might be a little bit steeper in its slope than this one, but not much. But the big difference is going from 1 ounce to 2 ounce. You can definitely see that 1 ounce to 2 ounce, the young people tend to have it tends to affect the reaction time of young people more than, say, the middle-aged or older groups. So when we're making these comparisons from none to 1 to 2, again, we want to be doing that within these lines because that's taking into consideration the effect of age. All right, so let's go back to our notes here. Just pick up with where we left off. So that is getting the marking by columns. This is the graph that we were just talking about here. Again, wanting to make comparisons within each of those groups. And I think I'll stop here for this video, and we'll have another video that will cover the rest of the pages of handout number 7, part A. All right, thanks for listening.